Okay. So before I continue, any questions on the stuff that we had seen yesterday? No questions. Okay. So in which case, we will continue with what we are doing, right? So to give a summary, what we are doing is we had this type checking procedure that we had seen as part of simply type lambda calculus. And what we had seen is if you encode the type checking procedure exactly as it is defined, right, without any additional work in Prolog, you get type inference for free. For example, we can get the type of um, we can even get the type of polymorphic functions such as lambda f, lambda x, fx. I think I this okay. So I need to run the previous cells. Um, I might do that in the background. Let me do that. So you can run. You can. Okay, so let's let this run in the background. There are going to be a few cells which are going to take a few tens of seconds to run. But anyway, so we can get polymorphic types out for free, right? So the idea is that we have this type predicate, which takes a term, right, a lambda calculus term, and then gets you the type. But as we have seen over and over again in Prolog, right? So there is no input and output. All you're doing is querying the program. So the question, interesting question is, what if I give the type, but make the program a variable, right? And what Prolog will, I mean, the question sort of says that find me all the programs that satisfy a particular type, right? And this is quite a curious notion of um, programming essentially, and this broader concept of coming up with programs according to some specifications is known as program synthesis, right? And in our particular case, the specifications happen to be types. So we say, okay, what is that program? Give me a program that will satisfy this type. And and what we are going to do in the rest of this lecture is going to generate lambda calculus programs, right, in the same language that we've seen so far, which we will generate according to a particular type that is given. And as you can see, right, so we have this notion of the most general type for a particular program. So we can say, okay, if I give you a program, there is one best type for a program. But if you think about um, the uh, question, flip the question. If I give a type, is there one good program that has the type? And what is the definition of good there, right? So because the programs might have different behavior, so you can have all sort of interesting programs that return an integer. So it is not at all clear whether there is one program that you can generate, and the programs may be large and small, right? So the simplest program that I can think of for an integer type is just the program with 0, right? The expression is just 0 that has type integer. But you can also have a program that computes the Fibonacci number of, like, 100th Fibonacci number, right? That also returns an integer, and that also satisfies the specification, which is just give me a program that satisfies the type integer. So because we have a large class of these programs, what we will do is we will say, okay, rather than getting me all sort of programs, um, because the tree of possible programs is infinite, right? So what we will try to do is to apply our iterative deepening technique that we learned earlier in class, where we found the closest answer to this countdown puzzle. So here what we'll do is we'll find the smallest program that will satisfy a type. By smallest, I define the size of a program to be the depth of the abstract syntax tree, right? And for an expression 0, the depth is 0. And if you have complex expressions, you will have a greater depths. So what we'll do is this. So we will ask Prolog to generate programs, small programs first, and then bigger and bigger programs as we go along, right? So that is what we are going to do. Yeah, so as I mentioned, we are going to use the depth of the abstract syntax tree of the terms, right, in order to iteratively search starting from depth 0. So this is going to combine all of the ideas that we've seen so far. So in order to compute the depth, what we're going to do is start from some depth n, and at every step, we're going to decrease the depth, right? So in order to do that, I define this predecessor predicate, which holds if b is the predecessor of n, right? Um, and this is defined just as you would imagine it to be defined. So if n is greater than or equal to 0, then p is n minus 1, right? So that's there. We define predecessor. Now we are going to iteratively deepen our search space, right? So the thing that we want to do is to add this notion of a depth to our type checking rules. This is very similar to how we did the delta in the countdown example. All we are going to say is every rule now takes this additional depth. Okay, and what we are saying is let's look at this rule now, right? So let's start from arrow elimination. So this used to be the rule before. So it says that it gives the type checking rules for applications. In order to assign the type B for M applied to N under gamma G, right? Show me that M has type A arrow B, right? For some A, M has to be a function type and N has to be of type A, right? This is what we have seen earlier. And what is the new rule augmented with depth? So we have this D parameter extra, right? We say the type of application of terms M to N under gamma has type B with depth D. If DD is the predecessor of D, right? We decrease D by 1, that's DD. And we can show that under we use the depth DD for the recursive terms. Essentially, we say that for type checking, we will only explore up to certain depth. And because predecessor of 0 is not defined, that particular property will not hold. We won't infinitely, we won't go for depths beyond 0, right? So the idea is that our type checking tree itself is pruned at a certain depth. And this is how we sort of iteratively explore. So we and this is the same idea in all of the places. For example, if you start, if you want to type check, if you want to check that first of M, the term M has type A under the gamma D, then you compute the predecessor, a DD of D, right? That is one less than the current depth, and show me that M has type some pair type with an A. The first component is A. The second component, I don't care, right? We don't care about the second component. But the depth is DD. So we decrement one, and eventually for these rules, right, if you sort of look at what the base cases of these rules should be, firstly, predecessor must hold, right? And it only holds if depth is greater than or equal to 0. So we have to satisfy this with the given bound. Any questions on this? Okay, no questions. So what I'll do is so I've added depth here. Beyond adding depth, we are not doing anything interesting. And I do the same for the additional rules as well for integers and booleans and if then else and addition, subtraction, and so on. Okay, so we added all the clauses. Now we write a procedure for synthesizing programs, which is basically type checking with this gen function, right? Gen we have seen earlier, right? Gen generates all the numbers from start to end inclusive. So we start from depth 0 and we go up to depth 10. Even with depth 10, we get very large terms. And we take the depth and we ask if you want to synthesize a program P, right, for the type T, take some depth D, right, which might be between 0 and 10. Under an empty context, the program P should have the type T, and depth argument is just the depth argument. So that prunes the search tree, right? So we initially start with 0, and then we continue up to 10, and that's all we explore. Okay, so that's synthesis, and it's essentially type checking plus this iterative deepening, and this gen gives us the iterative deepening mechanism. Okay, so now we can synthesize programs. So what I'm asking Prolog to do here is give me all the programs P, right? I mean, give me first 1,000 programs that you can find for which satisfy the type integer, right? And if you run this, you get a lot of examples. All of these are programs that have integer type. So we see that we have 0, 1, right? We have 0 plus 0, which is an integer program. We have if then else, true 0, 0, false 0, 0. We also have start to see complicated programs, right? This is lambda x identity function applied to 1. This is lambda xx applied to 0 plus 0, right? And so on. So this keeps increasing, right? So this is quite good. So we are doing quite nicely, right? All of these programs have type integer. Integer is okay. So we are not integer as a specification is not that useful, right? So let's try to synthesize more interesting ones. So here is an interesting program, right? So here is I can believe that I may ask you to write this program in your say exam, right? So I can ask this a question where you say, "Oh, give me an OCaml program which has this type." Right? It takes a pair and then returns you the first component of the pair, and you will write, "Oh, it's a function type," right? So it takes a pair and then extracts the first element of the pair using first. So all Prolog knows here is just the type checking rules, right? And we are going to ask it to compute that particular program which has this type. So I've written that down here. I'm saying get me all the programs that satisfy that type. Let's see what Prolog produces. So Prolog produces 10 candidates. By default, we prune at 10, but it might produce more. Let's see what program it has produced. So Prolog says, I'll pick A to be unit type, right? And B to be some polymorphic type underscore 1592. And Prolog says the program that I've generated for you is a lambda x dot u, right? It's a constant function that always returns a unit value. It's quite strange, right? So if you sort of look at this type, you'll think that this is the only possibility for that. But what Prolog has done here is it has gone ahead and specialized A and B to concrete types, right? It has not concretized the type here, but it has concretized the type for A, which is what is, I mean, Prolog is sort of playing fast and loose because our specifications are not quite tight. We never told Prolog, okay, you have to generate a polymorphic program. We never said the Prolog you cannot specialize the type for A. So Prolog has just specialized the type for A, right, to be unit, and it has just generated a program which takes a polymorphic argument that could be anything, and Prolog says, oh, that could as well be A star B, right? I completely ignore it, and I just return unit type, right? And because A has been unified with the unit, this program actually satisfies the specification that we've given here, right? But I mean, if you read through the other examples, Prolog is trying to do the same. It specializes all of the, it specializes A, and then just gives you programs that return the same A. So this is valid according to the specification, right? We never told Prolog don't specialize A. Um, but what we are interested in is sort of this idea of a most general program, even though there is no one most general program. One nice property that we want is to preserve um, polymorphism, right? So we don't want Prolog to specialize A or B when we ask for Prolog to generate programs of this form. So when we ask Prolog, please generate a program from A star B to A, we want to also say that don't specialize A and don't specialize B, right? Don't assign, don't ground these variables, right? Um, in other words, types must be polymorphic. And the way you can do this in Prolog has some built-in predicates for helping with that. And there is a predicate called var one, which basically applies to a variable, right? And it says it only holds if the given variable happens to be a variable. It is not specialized to any other term, right? So what we ask Prolog to do here is we force Prolog to keep A to be a variable, maintain A to be polymorphic, keep B to be a variable, maintain B to be polymorphic, and ensure that A and B are distinct. So diff is another inbuilt predicate. We've seen diff as part of the cuts and negations class, right? So diff is similar. It says keep A and B to be distinct, right? Just so that we naturally capture what is said here. We don't want it to be A star A to A. I really want it to be A star B to A, right? So that's what I'm asking Prolog to do. And I'm asking Prolog to generate exactly one candidate for that. If you sort of stare at it, right, there can be only, I mean, yeah, so there is one good program for this particular type, and Prolog finds that program, right? So Prolog says A is some variable, B is also some variable, um, and the program that it is producing is lambda x first of x, right? Or lambda p first of p. And this is precisely the program that we were looking for, right? Lambda p first of p. And by adding suitable constraints for our program generation, we can get the necessary program that satisfies our intuitive understanding of what we are asking. We can also generate all sort of, as long as you can express the type and then express the constraints, you can generate keep generating interesting programs, right? So here I'm asking Prolog to generate a candidate program for which takes as input A star B star C and then returns a B, right? How do you get here? You need to extract the second component of the given input, right? And extract the first component. And we want all three ABC to be polymorphic and distinct. So, so that is what we do, right? So we just write down the type here and we ask Prolog to synthesize that program. We ask Prolog to keep these as variables, and we ask them to be distinct. Of course, you can sort of write a procedure, right, which takes a list of variables and then ensures that all of these are variables and all of them are distinct. I will leave that to you. Um, but I'm making a point here that we can generate interesting programs. This program is a little bit interesting, right? So it's, you have to search through the terms that you have to get the intended semantics, and the semantics is actually given by the type, right? By looking at the type, we are getting the semantics. And if you run this program, Prolog searches for a little bit, right, and then gets back with the answer, which is lambda x, lambda p, first of second of p, which is precisely the program that we were looking for, right? And of course, I'm only scratching the surface of program synthesis here, right? Program synthesis as an area is um, like very rich right now, and it's sort of um, it is also interesting now thanks to the revolution in machine learning and artificial intelligence, right? So we have lots of data-driven methods which we can combine with these um, rule-driven methods in order to generate interesting programs. Imagine a world where you can just write a specification. I mean, I've given you a lot of specifications in this course. You can also think about specifications for your, say, C program, right? Write a red black tree. We know what a red black tree is. We know what a red black tree property is, but we still have to write those programs. Imagine a world where you are able to specify the properties in some language. We use types as a language here, right? And with additional things here. But if you have a rich enough language where you can specify um, these constraints, and the program and the computer can automatically generate the program according to some specifications. We are not even considering uh, things about efficiency and so on here. But you can imagine if you have a rich enough language, maybe we'll get to a world where we can generate programs automatically, right? This is programming, but what you're doing is you're just writing the specification, right? We are looking at very simple. So the distinction that I want you to take away is that we are specifying the program. We are not actually writing the program, right? I'm not writing this function. The example here is very simple, right? And it is the structure of the type is closely matching the structure of um, the program, but you can imagine more interesting structure. I mean, as I said, I'm only scratching the surface. Think about the sorting procedure, right? It is much easier to describe what a sorted list is. I can say a sort procedure takes an input list, right? Returns a list where the membership of the list remains the same and the list happens to be sorted. Here, the specification is so much easier compared to actually sorting the list, right? So there are instances where the specification happens to be much smaller and well understood than the actual program. And here it's sort of it's so simple that you might not see it. But I mean, this is a very, very rich field, right? So again, um, program synthesis sort of just to give you more ideas, right? So um, it is it might seem like a easy way to just specify what we want from the program and then have the computer generate it. We know exactly what type that we want here, right? And we are saying Prolog, go generate a program of this type. Oftentimes, the problem in real world software development is we don't know precise specification, right? So there are also interesting methods that sort of generate synthesized programs based on input-output examples. So you'll say, you will give an input list and you'll show that it is sorted, right? You give several examples like this, and based on lots of cool techniques, we come up with candidate solutions that satisfy all of these properties. The interesting avenues are combining both data-driven techniques, pure data-driven techniques, search for things based on ML and AI, and these sort of deductive techniques, right? So it's a very rich area. Anyway, so scratching the surface here. But that's all I wanted to say about this lecture. Any more questions or comments or anything on this while I open up the next one? You can ask questions on the chat. I'll have a look. Okay, so I find no questions, so I'm going to continue with this lecture. Um, yeah, so this will be the last lecture. Okay, so I had two other lectures, but I think I'm way over time, and it's not useful to overload you with too much material in this interesting circumstances. So what I'll do is I'll finish with this lecture. So I'm hoping that we can finish this by this week. So what we are going to see in this lecture is graph search, right? A lot of the problems that you see in the real world can be translated into a graph search problem. And as we've seen with the last few lectures, we'll look at examples, right? We'll pick one example and then we'll keep on building upon that example to do more interesting things. So this example, this lecture is going to be just graph search, right? And we can start with a very simple graph search problem. So a part of what you will learn in this lecture is look at certain problems, identify that they are graph problems, convert them to Prolog, so that you can solve the problem in Prolog, right? So here is a simple maze, right? If I ask you to solve it, you will solve it very quickly. Um, and there are multiple paths in this maze, right? Not everything leads to the solution, the center. And the question is, okay, how do you solve this, right? And how do you make Prolog solve this? And that's what we are going to see. So the first learning goal for this problem is how do you take that maze and convert that to a graph search problem, and how do you solve that problem, and how do you handle cycles in the graph search? And oftentimes you will see that real world problems have cycles in the graph. We will look at how to handle cycles in the search path. So the technique here is to say, okay, every opening in this maze, I will label it, right? And I will consider that to be a vertex in the graph, right? So I have lots of labels here. Every opening is labeled, okay? And I will consider that there will be an edge connecting adjacent openings. So if I can go from, I can enter through A, right? And I can go to G and B. So I will consider that there is a path from A to B and A to G. And similarly, a route from B to C and B to H, and so on, right? So just to give you, like, if you sort of look at this solution, the solution is a path, right, which goes from A, B, C to D, um, D, J, R, and U. So that's the solution, and we will sort of search through this graph to reach the solution. And we will use the predicate root if B is one of the openings that is reachable on entering A, right? So you are at A, and if you can reach B, then we say that there is a route from A to B. And we will use this to encode this whole maze into a set of facts which describe the graph. So, so here is the actual graph, where you can see that there are different paths, right? And if you draw that out um, as a tree, right, you'll get this tree. So observe that you can go from A, B, C, D, J, R, U. So that is one path, A, B, C, D, J, R, U. But there are other paths which are not reaching the goal, right? The goal is U. U is the, and U and T are ends, but really U is where you can reach. Even though there is a T, you cannot reach T from the opening vertex A. Okay? And if you look at this, T is not reachable from A. Right? And this is all the paths that are reachable from A. And this is what we are going to do. And I encode all the graph edges as facts, like nodes. We just encode um, nodes as atoms in Prolog. So I load all of these clauses. I get 15 clauses, which correspond to 15 edges. And now root is sort of capturing one hop, right? And you want to capture the notion of traveling from the start to the end. And the way we do that is define this predicate called travel, which holds if you can travel from some node A to some node C. And there are two ways to travel, right? If you can travel always from the current node to the current node. So you are already there. And you can travel from A to C if there is a route from A to B, right? And you can travel from B to C. So this is basically transitive reflexive closure defined using Prolog clauses. Okay, so we define the travel clauses, and then we describe what is the start and end start and finish nodes. We say start of A holes, that's the start, and finish of U holes to say that that is the finish node. And we define this clause called solve, where we say, okay, you have to start at some A, you have to finish at B, some B, right? And you have to be able to travel from A to B, right? So I encode all of these facts, and if I ask Prolog to say, can you solve this? Prolog will say, okay, true, right? So of course there is a path. And Prolog has internally solved this, right? But we are not getting any useful rule because when we solve a maze, we actually want the path from the starting node to the center. And the way you can do this is you can attach a log to remember the route that you've taken. So I define the predicate travel log, which maintains the list of paths that were traversed, right? So if you travel from A to A, there is no path, so the list is empty. If you travel from A to C, you can travel from A to C. If you have a route from A to B, and you can travel from B to C, right? And if traveling from B to C gives you the path steps, right? Steps is the list of steps. Then traveling from A to C will have one additional step, right? It will have the step from A to B because that's the step that we have here. And now we are remembering the actual traversal in this list. So now you can solve for the particular path, right? So what we are asking here is there a solution where the path is L such that you start at A, start was defined earlier as the vertex A, and finish at some B where you finish was defined as U, and the travel log from A to B happens to be L, right? So that's why we have this L variable here, which in order to get out the path. So if you do this, this gives us A, B, B, C, C, D, D, J, J, R, R, U. And if you go here, this is the same as A, B, B, C, C, D, D, J, J, R, R, U. Right. So that's the solution that we were looking for. Right. We got both the fact that there was a solution and the fact that what the solution was. Any questions on this so far? Okay, no questions. So let's make this problem more interesting, right? So let's add a new opening. So if you look at this one, I've created a new opening here, and I named it V. And the reason for doing this is we are introducing cycles in the graph. Yeah, Venkat is right. So that's precisely what I'm doing right now. The earlier puzzle, the earlier maze did not have cycles, right? But now I'm explicitly introducing a cycle, and you can see that there is a path from A, B, C, D, V, Q, and then PI, and there's a path here, right? If you go down this route, you'll get stuck. And if you think about how Prolog does resolution, right? How Prolog computes, it is doing a DFS, right? So it is going to get stuck if it enters this path. If it is unlucky enough to enter this path, right? We don't know whether it will certainly enter it. We know that it will get stuck if it goes through here. So we want to avoid this, right? We want to handle cycles. How do you do cycle avoidance in a typical graph traversal? You will have this notion of visited nodes, right? You will mark nodes being visited, and you will prevent visiting the nodes that you previously visited. You'll do the same thing here. So I've added a cycle. So what happens here is now there is a path from CD. The solution is down this path, but now you can enter through here. You can go QVD or QVD, QVD, so on. There are going to be like these two problematic edges that I'm going to add to the previously added edges. So I'm going to add a path from Q to V and V to D. Okay. So I'm going to add a path from Q to V and V to D. I'm not going to run this because this goes into an infinite loop. You can try this out yourself. Okay, so we have to handle this somehow. So what we are going to do is to remember the visited nodes, right? So I define a travel safe predicate now, which does not have the log right now, but it only remembers the visited nodes. And travel safe of AA holds regardless of what the visited nodes are, right? And travel safe of AC holds with the visited node visited, right? If there is a route from A to B, right? And B is not a member of the visited set. So there are two things going on here. Member is a built-in predicate. You can define membership yourself. It is not. At this point, you should be able to define it yourself quite easily. Member is going to check whether the given term is a member of this list, right? It holds then. And recall that backslash plus we use for negation, right? It's just not. So what we're saying is there must be a route from A to B, and B should not be part of the visited set. And we can B is not a visited part of the visited set, and we can travel from B to C, right? And we update the visited set to include B, right? Because we are going through B, we are augmenting the visited set with B as the head. So if you do this, then you can solve the given puzzle, right? So this just returns true, and we are not we don't have the log here, but if you but you can attach a log to this as an exercise, right? So we've seen how to do logs before. So we've handled cycles as well in this, and that answers Venkat Rao's question. Okay, so any questions on this so far? Okay, this is it's maybe quite easy because you've seen enough of prologue right now. Okay, so let's move on, right? So it turns out that a lot of the problems that you see, right, in the real world are sort of if you stare at it, you can sort of think about them as graph problems. And here is a like a famous puzzle, the standard puzzle. There are many names for it, but we'll just use missionaries and cannibals as the name for it. So the puzzle is, I mean, you might have heard of this puzzle earlier, right? So there are 3 missionaries and 3 cannibals and 1 boat who are on the left bank of a river, right? The boat carries 2 people, um, and the intention is to take all of them to the right bank. And the catch is that if on any one bank, if there are more cannibals than missionaries, then the cannibals will eat the missionaries. Okay, so you want to safely take all of them to the other bank. So the question is, can you take all of them to the other bank? And if so, what is the actual set of steps that you have to follow in order to take the missionaries and cannibals to the other bank? This is a very standard puzzle, right? And we'll see how to solve this puzzle using Prolog. So in order to approach this problem, right, you have to start with some structure that captures the notion of cannibals and missionaries and the left bank and the right bank and where the boat is and so on, right? So what we will do is basically define this as some state which encodes all of the facts that we know about the state of the problem, right? And we will describe the puzzle as a state transition system. So you can go from one state to the other state according to whatever is allowed, right? And we will see that some states are safe and other states are not safe. You can only step through safe states, right? And given a particular state, there are possibly multiple outgoing edges options for the next state. For example, here, right, I have three cannibals and three missionaries. So I can take this is a safe state, right? Cannibals and missionaries are all equal, so that's safe. If I take two um, missionaries on the boat to the other bank, the cannibals will eat this missionary, right? And that's an unsafe state. There's a possibility of doing that, but that is unsafe. But I can take, say, one cannibal and one missionary, or two cannibals to the other side, and both of those lead us to safe states, right? So the question is, what we are going to do is to enable these as some configurations and a state transition system, and we will let Prolog explore the state transition system to get to the intended final state, which is all of these folks are on the other side safely, right? Without anyone having eaten anyone else. Okay, so the configuration that we will use for this problem is, I'll just call it config. Um, it's a function with 5 arguments, right? Prolog function with 5 arguments. Um, and the arguments are that it contains the number of missionaries on the left bank, the number of cannibals on the left bank, number of missionaries on the right bank, number of cannibals on the right bank, and then the position of the boat on the bank, right? It might be left or right. So the starting configuration, right? I write start predicate for this configuration is going to be three missionaries and three cannibals on the left bank, 0 missionaries, 0 cannibals on the right bank, and the boat is on the left bank. So this is L. It is deceptively looking like 1, but that is L. And the finished configuration that we are interested in is um, there are 0 cannibals and missionaries on the left bank, right? And there are 3 cannibals and missionaries on the right bank. And I don't care where the boat is. So the boat might be anywhere. I mean, it has to be on the right bank, but that's not important. Okay, so let me add those two clauses. I think it's already added. Let me restart and clear output. So let me add these. Oops. Okay, so now if I add this, okay, I added two clauses now. Okay, and then so not every configuration is safe, right? There are configurations where the cannibals will eat missionaries. So what is a safe configuration, right? A state is safe if no missionary gets eaten in that given state, right? A missionary gets eaten if there is at least one missionary on that bank and the number of cannibals on that bank outnumber them, right? There has to be at least one missionary, and the number of cannibals on the same bank outnumber the number of missionaries. So we say that these three clauses are defining the safe states. So what does this say? So if there are no missionaries on the left bank, I don't care what the number of cannibals on the left bank is, because there are no missionaries to be eaten. If there are M2 missionaries on the right bank and C2 cannibals on the right bank, it better be the case that the number of missionaries is greater than or equal to the number of cannibals, right? That's the safe state. And similarly, for we do the same for left bank. Let M1 be the number of missionaries on the left bank, C1 be the number of cannibals on the left bank. If there are no missionaries on the right bank, I don't care what the number of cannibals on that bank is, but I do want to make sure that for safety, the number of missionaries on the left bank is greater than or equal to the number of cannibals on the left bank. And these are handling the cases where there are no missionaries on the left bank, left and right banks. I don't care about what the number of cannibals is. But in case these two are not true, right? So we can have missionaries on both the banks. and cannibals on both the banks. And we want to ensure that the number of missionaries is greater than the number of cannibals on that bank. Okay, so that's safety. So we define three clauses for what a safe state is. Okay, so that's the that is giving us safety for a particular state, right? Now we need to define the transition between states. So how can we transition from one state to the other? A boat can carry a few people, one or it must be either one or two persons from one bank to the other, right? So we define this predicate called carry uh, that is parameterized with the number of missionaries on that boat and number of cannibals on that boat, right? So you can carry, the boat can travel if there are two missionaries, no cannibals, one missionary, one cannibal, two cannibals, one missionary, or one cannibal, right? So there are 5 possible ways to transition from um, one state to the other, right? Not all 5 are possible all the time because there might be no missionaries or cannibals on one side to satisfy all of these. But these are the all 5 possibilities, right? So that is added as well. And now here is the state transition system, right? So this is defining, given a configuration, how do I step to the next configuration? Okay. So we have 2 clauses here, right? And the 2 clauses are going from left to right bank, right? And this is going from right to left bank. Okay, so that is why we have 2 clauses. And what are we saying? So I'm using variables in a suggestive manner. So these are the way you should read this is the number of missionaries on the left bank at the beginning, the number of cannibals on the left bank at the beginning, the number of missionaries on the right bank at the beginning, number of cannibals on the right bank at the beginning, and similarly number of missionaries on the left bank at the end, right? Number of cannibals on the left bank at the end, number of missionaries on the right bank at the end, number of cannibals on the right bank at the end. So we are going from the begin state to the end state, and these are the variables that I'm using. So how do we do this step, right? So let's take a configuration, the start configuration, and this is going to be the end configuration. You can go from start to end if you can carry MC, some number of missionaries and cannibals. So if you are carrying M missionaries, it must be the case that, and we are starting from the left bank, right? So this is left to right. So if you are carrying M missionaries, it must be the case that the number of missionaries that you had on the left bank is greater than or equal to M, right? If you are carrying M missionaries by board from left to right bank, it must be the case that you at least have that many missionaries on the left bank, right? And similarly for cannibals, we use the same idea. So it must be the case that there are at least so many cannibals on the left bank, right, as they are being carried on the boat. And what happens when you carry people, right? The number of people on the left bank will reduce and the number of people on the right bank will increase. So that is what we write here. So the number of people on the left bank in the end state is the number of people on the left bank in the beginning state minus m, right? We carried m people, so that is minus m. And similarly, we will increase the number of people on the other side. So the number of people on the right bank in the end state is the number of people that you started with on the right bank for missionaries, right? Number of missionaries on the right bank at the beginning plus n. So we carried so many people. And similarly, we do the same thing for cannibals. And this rule is just for the other direction travel, right? So we just use the variable names appropriately. And you should be able to read it through yourself. So the point here is there might be multiple carry possibilities, right? If there are 3 cannibals, then 3 missionaries, I can carry 0 missionaries or 1 missionaries, or 2, right? So this defines multiple outgoing edges in the graph. Okay, I've added that. Uh, any questions on this? I think I'm very close to the end, so I'll finish this lecture quickly today. Okay, so and then we now have defined all the necessary steps. Now we can actually define travel. So just like before, we can travel. Travel is a predicate that has four components. So start configuration and end configuration. The set of visited nodes, because you can keep going back and forth with the same set of people, right? You can go from safe state to state. We don't want Prolog to go in this infinite loop, so we have the visited configurations as well, and we also keep a log of the steps that we do. So we have a log as well. So we can always travel from the current state to the current state. We can travel from a state A to state C if you can step from A to B, where the step predicate is the one that is defined here, right? And B happens to be a safe state, right? The target state happens to be a safe state. The target state is not one of the visited states, and you can travel from B to C, right? Where A and B are both visited, and then you have the rest of the steps, right? And the result will contain B as part of the steps that you visit. Okay, so if you do this, then we can now write the solve procedure where you start at some state. Recall that we've already defined what the start state is and the end state is, finish state is. And we should be able to travel from A to B with initially no visited states, and the result is going to be L. That is what we push out here, right? And solve for is only here just so that the result becomes is formatted nicely. Okay. So I'm not going to explain the details there. It's just a matter of presentation. So you can ask for the solution. The solution says that you start from the configuration, which is 3300L. Both all the cannibals and missionaries and cannibals are on the left bank. Then you move to configuration 2211R. The meaning is that you take one missionary, one cannibal on the boat to the right bank, and the boat is now on the right bank, right? So you can read this that way, and we get this final configuration, which is 0033R, right? The solution is the same as what is given in the Wikipedia for this problem. This Wikipedia calls this jealous husband's problem, but you can sort of see that in the same way. So there are three missionaries, three cannibals. Initially, you take one missionary, one cannibal to the other side. Then you bring in one missionary over to the left bank, and you keep doing this. These are cannibals. The blue things are cannibals, and you'll see that the solution that we have here precisely corresponds to the solution that is presented for this problem on Wikipedia. So what we've done is we have solved the missionaries and cannibals problem um, by encoding them in this generic way um, in Prolog, right? So this solves a particular instance of the problem, but you can imagine for n missionaries and n cannibals, this will just work, right? We just use the 3 and 4 as 3 and 0 as 3 and 3 as numbers. You can solve it for any numbers. So yeah, so there are lots of problems that fit this pattern, though they might not appear to be graph problems in the beginning. Another example is Towers of Hanoi. I suspect that you might have heard about this problem. Um, so the idea is that there are these pegs, right, from the starting state, and you want these pegs to be in the same order in the ending state, and you can only move one peg at a time, and you want to get to the ending state. And the question is, what are the series of moves that you can do with this intermediate temporary state to get to the final state, which is all the pegs are moved here. If you stare at it, it sort of you can sort of encode the same problem in the same way as how we've encoded the missionaries and cannibals problem, and you can try this on your own. So I'll stop here, and I think this is all I wanted to cover in this course. So I hope that the course was as enjoyable for you as it was for me, right? So and I suspect that I haven't decided about the final exam yet, because it becomes quite tricky to run the final exam remotely for this course. I haven't made a decision. It is likely that you won't have a final exam this year, right? So I haven't made a decision about it. It'll be start of the next semester, hopefully. If the situation changes, otherwise we'll figure out what to do. I'll give you sufficient time before I announce the exam, right, so that you can prepare for it. And if it happens to be a remote, then open book and all the rules apply, right? So we'll see what we do. Anyway, so any questions on this? Otherwise, I'll stop here. And you can continue asking questions on Slack. I'll hang around on Slack and answering questions about the assignments as well. Okay. Thank you very much. Yeah, thanks to everyone for making this enjoyable, even in this weird time, right? I haven't met any of you personally, so hopefully we will meet all of you when this thing ends, right? And it'll be nice to meet every one of you. And let's make sure we meet each other. Thank you very much, everyone. Yeah. Stop presenting.